Hi, everyone. We're now actually going to construct these confidence intervals. So for example, remember our previous example with our TA Igor, who helped us grade a math test in a big lecture class. We asked Igor, based on the 5 exams that you graded, can you give me a confidence interval for the true population mean for the class after all 1,000 tests are graded? And then Igor might say, Master, I am getting a confidence interval between 70 points and 78 points with 95% confidence. So this is a 95% confidence interval. So how do we actually construct something like this based on sample statistics? All right. In lesson 28, we're going to estimate, for example, provide point and interval estimates for a population mean mu in this unusual case where sigma, the standard deviation, the population standard deviation, is known. Now you might legitimately ask, well, if we don't know the population mean, how can we know the population standard deviation? That's a good question. And we'll address this kind of issue in just a moment. But for right now, let's just say that the theory and the procedure is more natural in these cases. In particular, we can use a z-distribution to construct confidence intervals in this situation. Of course, the more common situation is where sigma is unknown. That's where you use t-distributions, and that's going to be later on in lesson 29. Okay, so in lesson 28, we're going to estimate a population mean mu if sigma, the population standard deviation, is presumed known. And we're going to use the z-distribution to construct confidence intervals for mu in this case. All right. So what are the assumptions here? In this lesson, we're going to find a confidence interval for mu, the population mean. And we describe these as 1 minus alpha confidence intervals. That's the typical notation. Because remember, 1 minus alpha corresponds to this region in the middle, this white region in the middle, the probability or area inside this white region over here, the area. And then alpha, the complement, is the total in the two tails. And often in actual tables or with software, you use alpha or half alpha to figure out what these critical values are. Anyway, we want to find 1 minus alpha confidence intervals for a population mean mu. What was the most common confidence level? The most common confidence level was 95%, or 0.95. But we also see 90% confidence intervals, 99% confidence intervals, 80% confidence intervals. Why not? But it should be a high confidence level. Okay, we're going to assume, and this is a big assumption, that the population standard deviation sigma is known. Again, this might seem unrealistic to you, but we're going to assume this for now. And we're going to assume, here's another big assumption, the central limit theorem, the CLT for means, applies. We're going to need this. And when does the central limit theorem apply? When one or both of the following is true. If the Big Daddy distribution is presumed to be approximately normal. Remember, we dealt with examples before with IQ scores, where we assumed that the overall distribution was about normal. Then the CLT kicked in immediately. It didn't matter how big your sample size was in terms of our ability to apply the CLT. We can apply the CLT regardless of sample size, in principle, if the original Big Daddy distribution is about normal. But if the Big Daddy distribution is perhaps unknown, or we cannot presume it's normal, maybe we're talking about dice. The distribution for one die result is uniform, discrete uniform. Remember that? That wasn't normal. So if you don't start with a normal distribution, all right, then you're going to have to rely on having a large sample size. The convention is the sample size would have to be greater than 30 if we're not allowed to assume approximate normality in the Big Daddy distribution. The 30 does not come from algebra. It just comes from practical observation. But in order for the CLT to apply, we either have to start with a Big Daddy distribution that's about normal, or in the absence of that, or if you're not sure what distribution you're starting with, then you'll need to rely on a large sample size in order for us to be allowed to apply the central limit theorem. So again, in this section, we're trying to find confidence intervals for a population mean, where the population standard deviation is presumed known, and the CLT applies. In a way, this is also kind of an assumption. It's our goal. We're estimating a population mean mu. Okay. What's our formula? It ultimately comes down to this. And you'll find this in many books, just written straight out. Our confidence interval for a population mean mu, again, remember, it's got to be centered at the sample mean, x bar. Okay. Remember our picture before for test scores, right? Here's our confidence interval, Igor's confidence interval for mu, the overall mean test score for the class, the population mean. When Igor graded 5 tests that were randomly sampled, he found that the sample mean was 74 points, and that has to be at the center. That has to be at the center of any confidence interval we form for the population mean mu. We require symmetry about the sample mean, 74 points, for a CI for mu. X bar has to be at the center. Give or take E, this margin of error, which is given by this formula over here. Now, of course, this formula here, if I were to just throw this at you, you might freak out. It might be easier to look at it this way. Again, our confidence interval for mu, the population mean, is centered at the sample mean, x bar. The mean, the population mean, we believe, is the sample mean, give or take this margin of error, E. I'll put this in blue. This margin of error, E, where E itself is given by this formula. And then when you put these pieces together, then you get this formula on the bottom. A confidence interval for the population mean mu is given by the sample mean, x bar, which is at the center, give or take this margin of error, E, which is given by this formula. And why does this all make sense? Because, again, the CI for mu, a CI is my abbreviation for confidence interval. It's an acronym. The confidence interval for mu has to be symmetric about x bar, the sample mean. Remember this picture over here. We need symmetry about the sample mean, here, the 74 points. And what's the deal with this formula for the margin of error? Well, take a look. We have this z-score. Notice that notation is the positive critical value. That z sub alpha over 2 is the positive CV, the positive critical value. So for example, so here, generically, it's over here, the positive critical value for the z distribution. If you want alpha total in the two tails, we split the alpha up into halves by symmetry. Okay, for a 95% confidence interval, anytime we want a 95% confidence interval where z is involved, we're going to want 1.96 as our positive critical value. And the plus or minus in this formula also automatically picks up the negative 1.96, the other critical value. Okay, so the margin of error consists of, all right, this positive critical value times this piece over here. I'll put this in purple. And where did that piece look familiar? Where did that piece look familiar? The sigma over root n. Where did that come from? The sigma over root n. That came from the CLT. That's why we had to make sure that the CLT even applied in the first place. Because, remember, this is the standard error for the mean, right? It's the standard error for the mean. The standard deviation of that x bar distribution we were talking about way back when. All right, sigma over root n. So it kind of makes sense then. Of course, the confidence interval is centered at the sample mean, x bar. And then for the margin of error, we have this positive critical value. That's how the confidence level influences the margin of error and therefore the confidence interval. The confidence level tells us what this positive z-score is. And remember, the larger the confidence level, the larger the positive critical value is. Remember, for a 95% confidence interval, the positive critical value for z was 1.96. For a 99% confidence interval down here, the positive critical value was all the way up to 2.58. So the larger the confidence level is, going from 95% to 99%, say, the larger this positive critical value is. So then the margin of error will be bigger. This half width here will be bigger. Because for a larger confidence level, we're going to end up with a wider confidence interval. And then this piece, sigma over root n, the standard error from the central limit theorem. All right, so how do we get the limits for the confidence interval? It makes sense. You start the sample mean in the center. You start the sample mean in the center, and then how far do you walk to get the lower limit and the upper limit of the confidence interval? You walk z, this positive critical value, z of these standard error pieces away. So you start the sample mean, x bar, and informally, you're walking z standard errors away, whereas the z-score here is the positive critical value. For a 95% confidence interval, you walk 1.96 standard errors away. For a 99% confidence interval, you walk 2.58 standard errors away to get the limits. If you didn't quite get that, we'll do a particular example in just a moment. By the way, before we do our example, a rounding rule. Because when you work out the margin of error, you're probably going to get a long messed up decimal. What's the rounding rule for rounding off the margin of error? And this ends up leading you to round off the limits for the confidence interval. Like over here, the limits were 70 points and 78 points. The rounding rule for the margin of error, E. You round off the margin of error, E, to the same number of decimal places as the given value of the sample mean, x bar. So for example, if the sample mean is rounded off to 2 decimal places, you round off E, the margin of error, to 2 decimal places. And then the limits of the confidence interval will also be rounded off to 2 decimal places. If you want to be conservative, basically playing it safe, and often in statistics, we want to play it safe. We want to be conservative. That's not a political order. Okay, it's a statistical piece of advice. When in doubt, be conservative. Play it safe. You don't want to be sued. And if you want to play it safe, round up the margin of error, which has the tendency to widen the confidence interval. Because remember, if Igor is saying, I'm 95% confident that this confidence interval contains mu, the actual population mean for the class. Well, if Igor wanted to be safe, okay, then Igor might want to extend this out. Okay, maybe it's better for him to say from 69 points to 79 points, so that the true population mean turns out to be 78.5 points or 69.5 points, then we won't sue Igor. I don't think we'll sue our TA, but hypothetically, we could sue our TA if the true population mean is not in the confidence interval. All right, so if Igor doesn't want to be sued, he might want to play it safe and move out the limits a bit. Play it safe. Raise the margin of error a bit and move out the confidence limits, the limits of the confidence interval a bit, within reason. Because I mean, if you were to go out to like 0 points to 100 points, yeah, that's a 100% confidence interval. That's not what we're aiming for. The idea is that we're asking Igor to give us a 95% confidence interval, so the confidence interval he gives us should have a confidence level of about 95%. It might actually be a bit higher in practice. Like if he tells us that the confidence interval is in fact from 69 points to 79 points, then maybe that's actually maybe a 96% confidence interval. Okay, close enough. But if you try to give a 100% confidence interval, you're making it too wide. Okay, but anyway, if you want to play it safe, round up the margin of error. I'm not going to make a big deal of this, but in statistics books, you're sometimes told to play it safe so that you're not sued, for example. And if you want to play it conservative, if you want to play it safe, you want to round up the margin of error. But if you round off, I'll be fine, as long as you do it to an appropriate number of decimal places, namely the number of decimal places that x bar is rounded off to. Wow, I just did a lot of talking. I'm going to refer back to all of this when we do our first example next time.